We come now to a particularly exciting part of the schedule, which is the contributed talks. So we'll have some shorter talks, so a more quick-paced session. We'll start with Raphaël Urfin from ENS in Paris, who's going to tell us about why diffusion models don't memorize. Raphaël, thank you very much.
So hi everyone. So my name is Raphaël from ENS. I would like first to thank the organizers for giving me this opportunity to discuss this work we did with Tony Bonner and my supervisors, Giulio Biroli and Marc Mézard, on why diffusion models don't memorize and the role of implicit regularization in the training dynamics. So my presentation is going to be threefold. First, I will briefly present what diffusion models are. Then I will discuss what I call the memorization and generalization regimes. And then I will finally describe our scenario for the regularization in the training dynamics of diffusion models. So you probably all heard about diffusion models. So it's a class of generative AI that has achieved state-of-the-art performances in a variety of tasks, such as image generation. So you can give a prompt. So here I put, so people going to StatFiz next week, like a conference room in Florence in the middle of July. So you can generate high quality images, even videos now, and audio generation. And it's not just for, let's say, artistic purposes, but also for science. So nowadays, you can use diffusion models for weather forecast, hydrodynamics, drug discovery, and any science that needs to sample from high-dimensional distributions. And the theory of diffusion models is quite simple. So you have first a forward process. So you take images, data points, from your training set, and you apply a noising process. So for instance, an Orstein-Lebeck process. And so you noise the training points gradually, and you transform your data distribution into Gaussian white noise. And then there is a second process called the backward process. And so it's a reverse time SDE in a specific force field that is called the score function. So you start from Gaussian white noise, and then you apply this backward process, and you will end up with new samples from your target distribution. And the key problem of diffusion models is to estimate, to learn this score function. And in practice, if you know the probability distribution of your target distribution, you can estimate easily the score function because it is the gradient of the log of pt, where pt is the marginal low of x of t, so the noisy data point at time t. Okay, but in practice, this is unknown. And so if you want to, for instance, minimize the L2 norm between your model S theta and the true score, you can use what is called the 2D formula. And you can translate this minimization, this loss, into a denoising task. So it's a complicated formula, but the idea is that if I learn an optimal denoiser that learns how to denoise noisy samples of my distribution, then I have a good estimate of my score function, and I can generate new samples. Now, one point I want to stress out is that in generative AI, there is no benign overfitting. So benign overfitting is a concept in supervised learning where you can have an overparameterized model that achieves zero loss on your trained tests, but nonetheless has really good performances on your test set. But here, if you have a little bit of overfitting, then you will have memorization for generative AI. And in diffusion models, it's really clear because the minimum of your denoising loss for an overparameterized model is the so-called empirical score. So it's a complicated formula, but the idea is that it is the score associated to the empirical distribution. And so this will lead to memorization. So you will only generate data points that were present in your data set unless you have data sets of size n that scale exponentially with the dimension, which in practice is intractable. And now, so this was a theory. If you look at real-life diffusion models, so in industrial diffusion models like DALI, you can have partial memorization. So if you take a specific prompt, you can generate images that were present in your dataset. So there are several papers that try to do this. And another really interesting empirical paper is the one of Kadrodai, Stefan Mala, and coworkers, where they show that if you train your diffusion models on a large enough data sets, then you will have no memorization, and you will have a score that is going to be independent of the data sets you use for training, and then you will be able to train, to generate new samples without any memorization. So this begs the question, so why diffusion models memorize? Why don't they memorize? So what are those different regimes? And can you have a global picture for this memorization, generalization transition? So our picture is this one. So we're physicists, so we like phase diagrams. And so we constructed this sketch of a phase diagram. So the two axes are the number of parameters of your model, of your neural network, and the y-axis is the number of data points. So there is a first regime, so the large dataset size regime that we call architectural regularization. So it is the regime described by Katrodrey and Stéphane Mallard, where your model is not expressive enough to represent the empirical score function. Thus, you learn a regularized score function that will be able to generate new samples. And so you have this first transition line, n equals n star of p. So n star of p is a threshold that depends on your model. And what we show is that there is a large window where you can learn a score that generalizes. So we call this phase the dynamical regularization phase. And we show that if you do early stopping in the training dynamics, then even though your model is expressive enough, so you have a lot of parameters, even though your model is expressive enough, you will be able to generate new samples by doing early stopping of your training dynamics. And then there is a third phase, the memorization phase, where you don't have enough data points, you have a too large model, and then you cannot do anything, you can just memorize. So now I will start to describe this dynamical regularization phase. And what enables you to do early stopping and learn a regularized score is the existence of two well-separated timescales in the training dynamics. So here I'm plotting two key quantities of my diffusion model as a function of the training time tau. So first, I'm plotting the inverse quality, so the FID in the language of computer science. And I see that when I start to train my diffusion models, then the quality increases, the FID decreases on a timescale that I call tau-gen. Then I have a second timescale tau-mem that happens later, where I state that the fraction of memorized data points increases. And what is really important is that the difference between those two timescales scale as n, where n is the size of your data sets. And so you have a large window where you can do early stopping, and you will have you can generate high quality samples without any memorization if you early stop between the two timescales. So we did, yes?
Does the dimension of your inputs matter?
So here I'm fixing the dimension, my model. I'm just looking at the scaling with n, but yes, n must be larger than greater than the dimension, for instance, for Gaussian. So yeah, there is a dependency on d, but here I'm just looking at the dependency on the size of the dataset. So we did some experiments on real images. So we did it on Celeba. So Celeba is a dataset of faces. Then we used a UNet. So it's a classical architecture for diffusion models. So with like between 1 and 16 million parameters. We trained it with SGD. And here I'm plotting so the FID and the fraction of memorized data points as a function of the training time for different sizes of datasets. And I see that first the FID decreases, so I have images of high quality. And then the fraction of memorized data points increases, and the larger my dataset is, the later this memorization onset will happen. And then when I rescale everything, so in the inset here, I rescale the training time by n, and I see that all the curves collapse. And so if I do early stopping before the onset of memorization, I have high quality samples without any memorization. So here, so on the two left columns, so the first column is the generated images for when I do early stopping, and the second column is the closest image in my datasets. And so I see that if I do early stopping, the generated images are far from the are different from the images of my training sets. And then the two last columns are the is for the model that where I trained too much, and I see that I collapsed on images I've used during my training, and so if I train too much, I have memorization. And so what we wanted to do was to find the simplest analytical tractable model that could explain this emergence of timescales. And so we decided to model our score with a random features model. So it's a well-celebrated model in the machine learning theory community. So it's a two-layer neural network where the hidden layer is fixed, so the weights are fixed, and I only learn the last layer, A. So W is fixed, A, I learn it, and sigma is a nonlinearity. And I train it on a denoising task, so I take Gaussian data points for everything to be tractable, and I train my last layer with gradient descent on n Gaussian data points that I have noised. And what I can show is that the training dynamics so the timescales of the training dynamics are given by the spectrum, by the eigenvectors of this random matrix U. And so this matrix, so xt nu of xi is the noisy data point nu with where I weighted time t during the diffusion, and I added noise xi. And so this is the covariance matrix in the feature space. So after multiplying by the first layer and the nonlinearity. And so we can study the spectrum of this matrix with the tools of random matrix theory. So for instance, the Gaussian equivalence principle. And what we can show in the other parameterized regime, so we have more, P is the dimension of the number of hidden layers. So I have way more hidden layers than data points than dimension. And I can show that the spectrum, so here is the density of eigenvalues. So the spectrum has two well-separated bulks. So here the inset is a zoom around 0. So I see that the two bulks are well separated. And I can associate each bulk to one of the regimes I discussed earlier. So the second bulk, so the large eigenvalues, will give me the generalization regime and will scale as order 1, while the small bulk will scale as order 1 over n. So will give me timescales order n, and this will be associated to memorization. Okay, so to conclude, we show that we try to understand the phase diagram of the learning of diffusion models, and so we show that there are several phases. So one where you are regularized by the architecture, by the finite expressiveness of your model, and another regime where you are regularized by the training dynamics, where I've shown that there are two well-separated timescales. And so if you do early stepping in this phase, you can prevent your diffusion models from memorizing, and you can enable generalization, which is the regime you want to be in practice. So thank you for your attention, and please feel free to ask questions.
Very nice work, thank you. Let's start at the back, I like that.
Thank you for the talk. Please, can you elaborate more about why you mentioned that in generative AI there is no notion of this benign overfitting?
Yes, so what I wanted to say is that in supervised learning, you can have zero loss on your training loss. So you have overfitted, you have because you are overparameterized, but then you can have really good performances on a test set. So it's like all the works on the double descent. But here, what I'm showing is that if you have zero loss on your training sets, then you have the empirical score. So, and this is the score that always memorizes. So having zero loss on your training sets is something that is not benign. It will always give a memorization. And so you cannot just have like a super large model, because it will lead to memorization if you're training too long.
Thanks. Let me come around.
So I just didn't understand in the last part how did you come to associate the first bulk and the second bulk to these two regimes? Is it some property of the eigenvectors, maybe of this matrix?
Yes.
But if you can tell us a bit more about this. And also, what do you mean? I'm a bit confused because your data in your model is some random noise, right? So what do you mean generalization in this case?
Yeah, really good questions. So here I'm plotting the, so on the left, the train and test losses for my analytical model. And you see that there are two regimes. So the full line on the left are the train losses, and the dotted lines are the test losses. And so you see first the two losses, train and test, are the same, and then they start to be different, and the train decreases, and the test start to increase again. And so you can associate each of those two timescales to the eigenvalues of my random matrix. And you can say that for the eigenvalues, eigenvectors of the second bulk, the train and test are the same. And if I look at the eigenvectors of the first bulk, then I will see the difference between the train and test. So it's you can see it's looking at the eigenvectors of each bulk, and you will see that the train and test are either the same or different. I don't know if it answers your question. Yeah, I guess. And then, it's fine. And then on the generalization, memorization, so you say, okay, I'm learning from noise. So how can I say that I have generalized? So for instance, the score for a Gaussian distribution is linear. So you can look, okay, how far am I from a linear function? And I say, if I'm a linear function, then I have generalized. And if I have some, I'm far from the linear function, then I have overfitted. And so here on this plot, I'm plotting the L2 difference between the linear score and my model. And I see that in the first regime, this difference decreases. It's almost zero. So the different cores are different sizes of data sets. So the first regime where I'm approaching the linear score, so the generalized score. And then on the second regime, this distance starts to increase again. And I call this overfitting.
Thank you.
Okay. One last question.
So are you saying that if I overfit, I always memorize?
Yes, for diffusion models, if you have a zero training loss, the only function that achieves this for a finite data set is the function that memorizes all the data points.
Okay.
I agree with that. Let's thank Raphaël again. And let's move to our next contributor.